Oh,
Hello everyone. Welcome back to Recording Lemeo. Right. Shall we begin? Shall we time that shit? Explain the difference between Amdahl's law and Gustafson's law. I don't even know if that is. You may use books, lecture slides, and laptop. So you can literally look this up.
it's
Well,
control
I mean,
method.
fucking if they're okay with it, Gustafson law. Hell, Gustafson law versus Ahmedal's law. This is way too scientific. There we go. If you focus on fixed computation cells, these code taking up sequential time. Massively parallel machines lab computational previously. Yada yada. Yeah. The speed up achieved by parallelization. Yeah, this is just like logic. Suppose you have an application taking time, TS, to be executed on n processing units. 1 minus f must be run sequentially. Yeah, fair enough. Okay, so yeah, one is regarding one is like taking a look at the speed up, and the I don't, wait. Increase problem size, speed up. Okay, so interesting that they have different speed ups. So one looks from the like way of the time. So they are talking about instead of 1 minus f times the program, they're saying 1 minus f times the sequential time. This still does make sense though. So my question is why is this number different from this number for the speed up?
I think one is, it says here in the book, it's for the special case that the sequential program has a constant execution time.
Oh yeah, focus on fixed computation problem size as just code taking a fixed amount of sequential calculation time. Yeah, okay, so that changes the speed up. A hypothetical run of task on a single core machine is baseline. It's theoretical slowdown of an already parallelized task if it's running on a serial machine. This is fucking based, by the way. This is true. If you get better shit, you don't just calculate faster, you just get bigger problems. So speed up in execution time the task on a single core machine. Huh. So what's the difference between the two? Okay, I'm just gonna like say Amdal Amdal's. Fuck, did I write that? Amdal's law assumes fixed problem size, while Gustafson's law shows the relation between problem size and speed up. Which I don't know if exactly correct. But,
I also think there is a difference that Amdahl's law takes the fraction as a constant, and Gustafson's law takes the execution time as a constant. I'm not really sure how, like.
Amdahl's law takes the fraction of parallelizable code to be constant, while Gustafson's law takes the execution time for serial, or for the serial case to be constant. Okay. Don't know how much of this is correct, and we'll never know because fucking XD. But it's good to think about anyways. Threads are lightweight processors, so OpenMP is always preferred. No. I love this about exams. They just give you such a fucking easy question because the moment they say always, you know that the answer is no. OpenMP is always preferred. Do you agree with the statement? No, because some programmers might prefer OpenMP. Bada bing, bada boom. Because like writing a short program in OpenMP is easier than MPI, because in MPI you're gonna have to like, well, that's not exactly true even.
You have to use pointers and references, and that sucks.
Yeah.
Maybe we need to look here at what are the advantages of OpenMP and what are the advantages of MPI.
So I think it is best for us to not Google or look at the books that much, even though this is an open book exam, because we won't have Google or open book. So if we can just get this from our own knowledge, that will be more beneficial to us, I think. OpenMP is always preferred above MPI. Do you agree with the statement? So when would MPI be better? I mean,
I think OpenMP, you can have the case that there's like a data race. So, and then MPI is a case. So that would be something.
I mean, you can have databases in both. Well,
no, MPI has a distributed memory, right? So you.
Yeah, that's true. You can't. You're right. So, but yeah, is this a positive point?
For it's the why you can use use MPI for OpenMP.
OpenMP. There are some cases where if you write your program wrong, MPI will deadlock, showing you that there is a problem, and OpenMP will just use wrong values, which might go by unnoticed. Furthermore, a developer might simply prefer MPI. Can you use OpenMP in Fortran?
Don't know.
Because I know you can use.
I think OpenMP you can use in Fortran, because I think he did give an example of that in, I think, lecture 2. If you look on the lecture 2 slides, I think it might be there.
OpenMP Fortran. Using OpenMP with Fortran, okay? MPI Fortran.
Sweet.
Okay, both can be used with Fortran. Okay.
Never mind.
Furthermore, a developer might simply prefer MPI. Yeah. I sometimes write languages in Python, or write things in Python, even though, like, it's not the fastest. You know, fucking, sometimes you prefer one, sometimes you prefer the other.
Yeah.
Like, yeah, just saying you should always use one programming language is just dumb. Okay. Consider a parallel computer of 2 to the k processors. What do a tree network and an omega network have in common? What are the differences? I have no fucking clue what the stats are of a tree network. We might be able to work it out
No.
though. So
Maybe they're both dynamic networks. I don't know.
yeah, they're both, but compare the two networks. Okay, yeah. So if these are
Maybe
two
we can-
questions, then one of these will be so they are both static. No, wait, one of them is static, one of them is
Dyna-
dynamic. Right?
Yep.
Trees are
Okay.
so
Right.
one
Trees
is
can be both. I think.
static.
Trees can be both dynamic or static. I think.
I don't think so. Let me have a look.
I don't.
Yeah, because trees are just static. Oh, so you can have every part be a node, or you can just have the nodes be at the bottom, and then use
Which
use the middles as switches.
Yeah.
So yeah, you're right. So I can go omega is dynamic. Trees can be both static and dynamic. Yeah. I don't know. For omega, do we get? I don't think we get degree, diameter, etc. Because that is not how you don't do that for
Anna?
dynamic ones. You get total number of switches, but that's it. Compare the two in terms of performance and cost. So trees require max 2 log p steps. Omega networks require log p steps. So where this 2 log p comes from is you need to go up the tree once and down the tree once. So I hope
Yeah,
that makes sense.
okay.
Since trees have log p, or I'm not sure if they have exactly log p. I think it's O log p steps for the tree. I'll just add O because never hurts, you know.
Yeah, that's true.
That was exactly
Uh,
correct, but it never hurts.
Doesn't matter because 2 is a constant anyway then.
Yeah, yeah. I could remove the 2, but like, yeah, because these two are the same, O log p and O t log
It's
p.
just the order.
So no, like the class O 2 log p and the class OP are exactly the same class.
Yeah.
Yeah, I'm just gonna say yeah, because it's max 2 log p steps, because it'll have more than that, and omega networks require max log p steps. Yeah, so trees can take longer. That's what this comes down to. What else is there? The amount of switches. So the amount of switches for the amount of switches in the static case for omega networks is p log p, and for a tree it is. So for a tree it is. Oh, that's actually really funny. It's p minus 1. Because yeah, so because you have say I'm going to my favorite program, Paint. So say you have here a total amount of n static nodes. Then you here have n over 2 and n over 4, etc. until 1. And this is a common known fact, or at least it's used quite a few times in computer science. So 2 to the n plus 2 to the 1 plus 2 to the dot 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 plus 2 to the n minus 1 is the same as 2 to the n minus 1. So yeah, that's how I got there. So if you have 2 to the Yeah, my notation here is wrong. It's I'm using here n as the amount of nodes. It should be the factor. But yeah, so because 2 to the 0 plus 2 to the 1, etc. Minus, or 2 to the n minus 1 is the same as 2 to the n minus 1, we can conclude that the amount of nodes in a tree that isn't the last phase, or the last one, is the amount of the last one minus 1. So I hope that's somewhat reasonable.
Mhm.
Okay, so so we have amount of switches, we have amount of steps. Do we have anything else? So performance and cost. So performance we have and cost we have. So I think we've answered the question. 4. A parallel program with a speed up of 10 using 20 processors. What's the maximum obtainable speed up if we can where we can use like a infinite? Okay, so this one is funny. So so say we have a program where so the time that it takes is 1 over, or it's time. Okay, I'm gonna write this in. So time b is time serial over b amount of processors. So time total is times f, where what we do, f is the serial percentage, right? So it's 1 minus f plus t
Fraction of the
times, yeah.
serial time.
So plus ts times times f. So right, say we take this, and we know that the speed up. Oh, let me just add some things so that it's actually readable. Oh, fuck off, Gyazo.
You just need to calculate what f is, right?
Yeah, which we can do using
And then
this.
just
So
do 1 over f.
S is t s over this entire thing. Wait, so that is speed up is this. So if we divide out the ts, we get 1 over p. Yeah, probably should put this in a fraction, but I'm very lazy. No, I really should. We have 2 fractions in one. Frac 1, and then this entire thing. Right, so this is the speed up, and we know that the speed up is 10, right, for 20 cores.
Mhm.
So okay, so the speed up is 10, and we know we have 20 cores, so it is 10 is 1 over 20 is 0.05. Okay, so we get this, then we swap around the variables. Am I not closing something somewhere? I think it's angry with me. Oh, that's why. And what we can do then is we can take this part, move it here, and put the 1 over 10 here, which turns to 0.1. And then we can pull this out of the brackets, and we get 0.05 minus 0.0 or minus 0.05f plus 1, so this becomes 1.0.05.
Processors
Oh, no.
20.
Mhm.
Sorry. Sorry.
Okay, no problem.
Just-
Plus 1 times f, so this is 0.95f. Yeah, okay, is 0.1. So we get, oh, that's not what I wanted to do. So we get f is, so this will become 0.05 over 0.95. So f is
I
that,
just did it in
which is 0.05 over 0.95. Oh, that's not a very nice number. Okay, we're just writing that as 0.05 over. Mhm.
I just put the, because it's only the f that you need to know. So
Yeah,
I mean,
f is
it's
0.05 over 0.95, which is 1 over 19?
Yeah, correct. That's
Lovely.
also what I had. For the,
Mhm.
Okay, So
Then
then we can
answer-
go back up here and we can say t total if p is infinite, this term falls away. So t
It's just
total
1 over f. So
is
then it's 19.
yeah, true. We know that already. So it's 19. Yeah, fair enough. Good call. Using Amdahl's law, we can say that the maximum attained speed up here is 19 times. Aha, look at me being fancy, using fancy words, being a fancy man. Right, 5. Consider a
God,
program
you're
of
so-
1,000 instructions. 4% cache miss rate, 25 are load and store operations. Holy shit, shut the fuck up. No, if one CPU clock cycle takes a half, what's the user CPU time? I'm just gonna try doing this by heart, just to see if I can. But
Yeah.
if this was a real exam, I would obviously go towards my slides. So
This is the
because
thing,
like
this is
this stuff is like
what-
very clearly in here, like oh yeah, but I want to see if I can derive this, right? That gives us knowledge.
Okay. I remember where this is, I think.
So 4% read and write cache miss rate. So that is 40 cache misses. No, so that's not true.
Relative-
Oh, so
Oh,
25.
yellow.
Okay.
Just do it out of your head, but I'll just check with the book.
Yeah, sure. So
If it's
since
listed.
so we have 1,000 instructions, which is 75% of these are normal instruction or are non-read-write instructions. Is 750. 25% are read-write instructions. Is 250. 4% of read-write instructions are cache misses. So I believe 4% of 250, 10. 10. 95% of read-write instructions are not cache misses, is 240. So, so we have 750 non-read write for 10 read write cache miss, 240 read write cache hit. Total time is TPI, where TPI is time per instruction, or TPI, so time per instruction is clock cycle per instruction times time per clock cycle is so clock cycle per instruction is one clock cycle. CPI is 1, yeah. One CPU clock cycle takes 0.5 nanoseconds is 5 times 10 to the negative 10 seconds. And now time to put many fucking double things because LaTeX formatting. Okay, so time per instruction is that. So total time is 700 or non-read write times TPI plus read write cache miss or hit times times TPI plus read write cache miss times miss penalty cycle amount times TPI. So total time should be 750 times whatever the fuck this value is, plus 240 times this value, plus 10 times 60 times this value. So it is 600 plus 750 plus 240. I probably should know this by heart, but I'm very lazy. 5090. So total time is 750, or this times this is, so I think Google will accept this if I just format it a bit. Right, 7.95 times 10 to the 7.5 times times 10 to the negative 10 to the negative 7. Oh god, now my negative 10 here needs to be in the fucking brackets. That's funny. Right, recompile, take this here, make this big. Oh, did it everywhere except for the last line. Oh, fucking, I forgot. So, fun fact, if you didn't know yet, percentage signs are ignore this symbols in LaTeX. So you have to escape them if you want to actually use them normally. They're common symbols, which I sometimes completely forget. So yeah, 70% are non-read and write instructions. Yeah, so this makes sense. Time per instruction is clock cycle per instruction per time per clock cycle. Total time is non-read-write amounts times time per instruction. Read-write hit per time per instruction. Read-write miss times miss penalty cycle amount as time per instruction. And that, yeah, I'm pretty confident that this is the answer they're looking for. I thought my logic was somewhat followable.
You know, I was looking in the book at the same time.
Later.
Fair enough.
So,
So yeah, the TLDR is that like every instruction that isn't the clock cycle takes the same, or isn't the cache miss takes the same amount of time. So yeah, the user CPU time is the amount of clocks or of instructions that take one clock cycle plus the amount of instructions that take 60 clock cycles times 60 times the amount of time per cycle. Yeah, it sounds very complicated, but it isn't.
in the book, like you can double check it in the book.
Yeah, true. So yeah, here it is. Yeah, so the read miss rate. Yeah, so this is what I'm using as well. So the amount of read operations times the amount of misses times the amount of misses per cycle. So read operations times misses is what I'm doing. I'm doing here. So where it is read operations times 4% for the misses, so that's 10, and then times the amount of cycles I do down here, where it's 10 times 60. So read write misses times miss penalty cycle amount. So that is yeah. So I do that. So yeah, pretty confident this is right. Lovely. Execution time of... Jesus Christ, how many questions are there? Okay, 10. Okay, that's better. We're over halfway. Execution time parallel is... This workload is 8n, and it's much larger than P. Oh boy, here I go calculating again.
Wait.
Right, this is the exact same question we've done 3 times before, so
Yeah,
we'll just do
you've
it
been
again.
doing this. Okay.
So right.
Ta-da. Oh,
They say repetition is how you remember, so
yeah.
if they now don't give us a question that has this, I want to speak to their manager.
Yeah.
TP is 17 n over P. I'll be nice and I'll use this fancy thing. Plus 2P. Overhead is TP minus, or C dot. You should use C dot. P minus W. I'll write down W just to be nice. W is 8n. So overhead is this thing, C dot P minus 8n. Do some calculations. This becomes fucking 17 times 2. I should know this. 34. Plus 2p squared minus 8n. So I'll remove this 8n right now because I'm lazy.
How do you have 34?
Because it's 7. You're right, this should be 17. I was multiplying by 2p, not by p. So this should be 9p.
Yeah.
Because it's 17 minus 8. Good catch. Yeah.
I have the same.
Yeah, lovely. So it's the overhead. Are they asking for the efficiency? Yeah, okay. When P increases, how fast must the other one increase?
Divided by 8n.
Yeah, so that is ISO efficiency is 9 frac 9n plus 2p squared over 8n. Let me just split this up. It's frac 8 over, or 9 over 8 n plus frac 1, so p squared over 4n. I think that the math checks out. Oh, of course, fucking. One day I'm not gonna forget that. $17 times A, yeah, that makes sense, and that's 9 over 8n plus p. Yeah, okay. So if n increases, or if p increases, how fast must n increase? So say p goes up by a factor of 2, n has to go up by a factor of 2 squared. Yeah. So if p goes up by a factor of a, n has to go up by a factor of a squared. I'll put you in brackets. I don't know if but in my way of writing it, I don't know if that's the way that they want us to answer it, but that is the way that I'm writing it. Yeah. Yeah, and that does mean that this will increase, but well, if programs are n increase, can I keep constant time? So n is much larger than p. Okay. Can I keep computing time constant by using more processor? So n goes up. If n goes up, can we keep p, or can we?
What is the question again?
They say if n goes up, can we keep the computing time constant by making p go up?
Like that's exactly the same question again, right? We're looking at again the
So I think the answer is no, because we're never dividing by p. So, funnily enough, I think for this equation, if I'm not wrong, more processors actually increases the ISO efficiency.
But do we not look again at the time? The one
Yeah, I think you're right again.
Same question.
Yeah, you're right again. You keep saying that. I keep forgetting it. The next question. Can we get computing time
Unit time
constant?
stays constant.
Yeah, the third,
Now,
driemaal scheepsrecht. Third time I'm not gonna forget it.
At least you won't forget it tomorrow.
I fucking hope so. Problem size n is increased. How can you keep your computing time constant? So n is increased. If we increase, so what did they say? Suppose n is much larger than p. Then yes. If n is large enough that the 2p term can be ignored, we can keep the time the same by scaling up p. P and the efficiency. What did I ask for? The efficiency, parallel efficiency, will stay the same. Right? Because like they say n is much larger than p. So if that's the case, then this time p is not going to matter in here, right? If we have 12 cores and 17 megabytes of data, then this 2p term is practically 0. So at that point, the parallel efficiency stays the same. That's where this answer is coming from. 7. Consider the following. Why can we not the parallel for to?
Before you start this, can I ask something regarding the first exam we did?
The first exam we did, sure.
Yeah, the answers are there, but I just don't agree with the answer of the teacher. But your answer was the same as his, so maybe can you do you have that file there?
We'll quickly go over it. We can see what you say and what I say. Which question are we on? Are you talking about?
Let me see. Go up. With the T0. Oh, I think it was that one. Or no, which question? This is the first one. So go down a bit.
This is the first one.
Yeah. Go down a bit. Sorry, it's question 12.
Question 12. Oh yeah, no. So
why? So my T0. Why do you have that p squared there? Because if I do, I have only p. There's no squared.
T0. So T0. It's not T0. It's TO. It's the overhead.
Yeah. Okay.
So the overhead is p times the parallel
times the processing time.
Yeah, and the processing time is p times square root of n. So if you multiply that by p plus this term, so if you if we're just looking at this term, because this term did p cancels off, we get p squared.
My TP.
P squared times square root of n. Does that make sense?
I think I had my TP wrong. Yeah, the TP. Yeah, it's everything there. Yeah.
Exactly.
My bad.
No problem.
Right, thanks.
You're welcome. That's what we're here for, to learn. Right. So, consider the following loop. Oh, lovely. We've got fucking data thingy, boys. Let's go. Can we use OpenMP? That's the nice one to use at least. Begin verbatim. Let's fucking do this properly. So first I can see output dependency. Like right down there. H is output dependency. So we have output dependency at H, which this is like almost exactly the example we gave, right?
Yeah.
Where you calculate something stored in a single number and then use that number again.
Yeah.
So the very first thing I do is I take this and I put it in here. Boom. Okay, that's one problem solved.
What did you do?
I took the variable h and just removed it. I took where they used h and just took the definition of h and put it right there. If that makes sense. So so the sin I y, I just put it in the place of h.
Yeah. Oh yeah, I see.
I used h as kind of an inline function, if that makes sense. So recompile. So what we do then is this uses. So this
Sorry to
line
backtrack.
is fine, right? This line doesn't have any problems with it.
Sorry to backtrack a little bit, but I think you made a mistake in the previous question.
Very possible.
On the last line, you didn't cancel out your n. With 9/8n, that's supposed to be cancelled out because it's cancelled out at the bottom.
You are completely right. So yeah.
Yeah, true.
That does even better because then this is like correct, which is always nice to do. Thank you.
No problemo.
Yeah. So here the last line completely problem free, right? We're not doing anything weird here. We're just calculating it using the value that already is there, but we're not using any kind of weird stuff to do with previous or future samples. As for this, we are using the one in the future. So, because we're going up, we can solve this by saying z is x.copy, and then every time we talk to something in the future, we exactly, you get it. Same thing as last time. And we've solved this. Now all we need is an OMP pragma parallel 4. And then if you really want to, we can even do a private eye. Bada bing, bada boom, it is parallelized.
Woohoo!
Yes, great. Lovely. Yeah, because X and Y are not like edited or accessed by threads that aren't its own threads, so there's no way this goes wrong. Lovely.
Yeah.
God, don't you love it when stuff comes together? Question 8. Oh, shut the fuck. Okay. Here we go. The 5-point central difference stencil into an m times n grid for a Gauss-Tridal SOR iteration. I'm feeling sore in my brain. The figure shows the areas of independent computation, starting at the top left. Yeah. So this is like, effects used in the order from the is minimum of m and n. That is so goddamn easy. That's just funny. Okay, I like that. So remember when I was like, oh, it's actually it's the square root of n squared of 2n squared, and people were like, no, it's actually just n because you can just move it up and it'll be n. Yeah, that's exactly the case here. So, the longest amount of points, or what do I call them, points? Is it equations? The longest amount of areas of independent computation is one of these diagonal lines. The maximum length of one of these diagonal lines is min n m. I hope I'm not going to have to explain geometry to them, because I'm very bad at that, honestly. Since the maximum... since we rely on since every iteration relies on all previous iterations, we can't, or since I'm gonna call them lines, fuck it, line relies on the previous line, we can't parallelize anything, any line ahead of the current one, so we will always only have n jobs, or at max n jobs where n is the amount of areas of independent computation on one diagonal line, which we know is, oh god, I used the wrong fucking variable. We can't use n because it's already in use. It's x, which we know is min n m. And if you have max, or it's not max, it's min. Min m jobs, you can at most use min m processors. Crazy, a whole bunch of shit that I'm saying, but I'm not really saying a whole bunch of shit. Right. Oh no, this min should be max. You have at max x jobs. Yeah, no, this is just logic. Consider the Gauss-Seidel iterative method to solve the synthesis of linear equations AXB, where X is a dense full matrix. Can we apply red-black ordering for the parallelization of the Gauss-Seidel iteration? So usually we did this because we have 5-point difference. So that will give the 5-point difference stencil gives us a tridiagonal matrix, I believe.
Yeah, because that's true. Then you have a sparse matrix, right?
Yeah.
Not a dense. We have a dense.
Can we apply red-black ordering for the parallelization of the Gauss-Seidel iteration? Honestly, I can write shit down, but there's a good chance it's guessed. I'm just gonna Google this. What is
I'm just looking in the book as well.
red-black ordering of
Most frequently.
Gauss-Seidel iterations? Yeah, I don't think this is in here. Could you check the book?
I'm scanning now.
Sure. In the meantime, I'll check the slides.
Blah blah.
It is lecture 7 that this is in. Oh, actually, it's pentadiagonal, not tridiagonal, which makes sense because you're going in 2 different directions, not just backwards.
But still, like now it talks about a dense one, right?
So, like right now, this is a non-dense one.
Yeah. I can't spot it in the book.
So for this, what you would use is you would calculate 9 here using 3 and 8 of the previous or of the next thing, and 10 and 15 of the current.
Yeah.
So honestly, then to go back to my question before, I think if you had 9 points, that would go fine, right? Because then you would use 2, 3, and 8 from the previous thing, and so because you would be using 4 and 14, which are currently being calculated. So then instead of being able to calculate this entire row, you have to calculate them one by one. So we were right, but for the wrong reason. Oh, that's actually good to know. Does what I'm saying make sense?
I'm reading still at the same time. Say one more time what you were saying.
You know the previous question where we had instead of 5 things around it, we had 9 things around it. So the reason that 5 things work so well is we can use a previous version, or we can use the already computed version of 3 and 8, and the previous version of 10 and 15.
Yeah.
At least if I'm reading it correctly here, because they're using the previous version, the iteration k minus 1 of these two, and iteration k of these two. So if we wanted to do that, we would suddenly also need 4 and 14, which were in the process of being calculated. So you would rely on other stuff that is happening during the same.
Yeah.
So we can't do 4, 9, 14, and 19 at the same time
Mm.
because they rely on each other. You would need to do
Yeah.
4, then 9, then 14 and 19. Either that, or you would have to use the version of 4 and 14 which are already there. But at that point, I'm not even sure if it's possible.
Yeah. I don't. So, does it say anything about dense matrices?
So let me have a look again. Solve a system of linear equations. Red-black ordering for the parallelization of a Gauss-Seidel algorithm. So the red-black ordering. Yeah, honestly, I think that we can. Yeah, so I don't see why we couldn't. Because like the this comes right after the pentadiagonal thing. But I don't know. Yeah, so this is not that like it is part of it. Yeah, I don't see why we shouldn't be able to. Yeah, I think a dense grid it would just work.
Let's go to the next one.
Actually, yeah, no, honestly, even with the slides, I'm not entirely sure. I feel like this was one of the lessons where I really should have been in a lesson, honestly. But I will. You only know that afterwards.
Try to do what? Can't understand what the guy says.
True. First fucking time.
True.
First fucking time I was there, I understood like barely anything. That was the moment I was like,
Nothing.
I'm gonna read from the slides. Okay, so
Yeah.
so
Like
8B.
one lecture, I was like, okay, I'm just wasting my time.
8B, I'm not very sure of, but the rest so far I'm quite sure of, which is very good because we're doing an open book exam, closed book.
And I also need to read anyway the slides of lecture 7 still.
Yeah.
So I'm also still take on that.
Consider a 2D Poisson equation discretized with a 5-point different stencil into n by n grid. God, why did I choose this minor? Suppose that a floating point operation take 1 unit and communication time takes 2 units. Suppose a parallel computer of 100 processes is used. What is the data locality ratio when stripe partitioning scheme?
Bruh.
I'm only slightly lying. Did look so the stripe partitioning scheme. So okay, let's go back. Jacobi iterations. What do they rely on?
I think it's again in lecture 7.
I think Jacobis are lecture 6. I could be wrong, but I'll have a look.
Because I did lecture 6, or I read through it, so I don't think it's in there. I think it's lecture 7.
Fuck, you're right. Okay, so iterative methods based on matrix splitting.
Jacobi iterative method.
So we begin with initial solution. Increase k. Take the diagonal matrix. Minus the fuck is R? Oh, R is this thing. Okay, R is a vector.
R is a row, I think, or maybe not.
Well, yeah, maybe, I'm not sure.
Oh,
8 is the most approximate. So that's the... Yeah, that's where we perform a matrix multiplication. I guess that... No, but we also do that here. I guess A is a full matrix, so that's more work than a... Yeah, this is a diagonal matrix, so...
Yeah.
Yeah, this is a full matrix, so that makes sense. So, the matrix vector multiplication, that's the defining task for a Jacobi thing. So, it's matrix vector. So,
Data locality.
if we do a striped partitioning scheme, so striped is a data locality is computing time between two consecutive communications over communication time on average. Oh, well, apparently it is 2c over tau. C and tau are the time of one calculation and communication. So it is... Tau is communication. So tau is... It's 1. It is literally 1. A, 1. B. They don't ask us to explain. Block partitioning. Oh, no, but this is not stripe partitioning scheme yet. Oh, no, it is stripe partitioning of A.
Yeah.
Okay, so let me think about the block partitioning then.
That's question B now, block partitioning.
Yeah, so first, let's try to make sense of what they're doing here, because they'll actually teach us something instead of copying the answer. So, N over P is the amount of stripes. So, one processor gets one entire row. So all it needs to do is first load... it needs to load the entire matrix it's multiplying by.
Mm-hmm.
Then it needs to load its own stripe. And then it does the calculations. And then it sends out its own row. So, its own... Okay, yeah, so this makes sense. So, n squared over p here, that is the data it has, right? So that is... Yeah, so it receives n squared over p, which is the data it needs to work on. It receives n, which is the data that it's going to work on, right? So that's the vector. So n squared over p is the matrix, because it only needs a stripe of the matrix. And n here is the vector, because it needs the entire vector. So
Yeah.
That times tau, because tau is the fucking the communication time. As for the calculation time, it needs to calculate n squared over p times n. So no, it needs to calculate oh, I see. So it needs to calculate n squared over p calculations to do just the multiplications. And then it needs to do n minus 1 over p additions. No, it needs to do n squared or n minus 1 times n over p additions. Jesus Christ. So this also makes sense, and I can explain it to you with a fucking visual, because holy shit, I'm just shouting numbers at this point.
Use the visual again.
Yeah.
I also think I just need to, for me, I just need to look through the slides as well, like, so
But
myself.
I mean, yeah, so it is still going to be useful to just know how this is calculated. And what better way to learn than to an example? So say you have this matrix, right? So say here P is 2. And, well, this thing should be a block, because it is 1, 2, 3, 4, 5, 6. Yeah, let's say n is 8, and this is a block, and I'm just too lazy to make the second half, right? So, whole block, crazy, right. So if let's make it P4 then, so that's easier to draw. So if I'm a core, the stuff that I need to work on is this. Right? and also the full vector next to it.
Yeah.
So the amount of stuff that gets communicated to me is entire vector n
Yeah.
plus this part, which is n squared over p. Because n squared is the whole matrix, we're dividing it over p cores, n squared over p.
Yeah. I see what you
So
mean.
that's the
yeah.
communication overhead, n squared over p plus n times communication time. As
Yeah.
for the amount of calculations, I need to do a calculation for every single field in here, which
Yeah.
is n squared over p. I also need to add them up for every single field. So that is, instead of for every field I need to do one calculation, I need to do for every field minus one for every, so I need to do one for every line here, right? Because the line is where two fields get added.
Yeah.
So instead of n squared over p, it's n, or n over p down, because n over p is 2 here, and n minus 1 over. So it's n
Yeah.
minus, or n over p times n minus 1. So calculate this out, you get n squared over p plus n squared over p minus n over p. That is very difficult to write, I'll rewrite it down here. N squared over p plus n squared over p minus n over p. Add this together, you get 2n squared minus n over p. And if we look here and we factor out an n over p, we get n over p times 2n minus 1 over p. No, not over p. So this. So this is just what we're saying up here, but then down here, right?
Yeah.
And now I'm gonna pray that my answer is correct. Let's go! So yeah, that's this here. So this makes a whole bunch of sense. And also my 1 is incorrect because it's doing more than just that. So it's not exactly 1 because this is an approximation. The answer is, what was the exact question? N by n grid, 100 processors. So n over 100 plus, or times 2n minus 1 over n squared over 100, n squared over 100 plus n, and this is times 2. So yeah, so if we multiply this in, we get over 50, 2n, remove this, and then we can like write this out a bit. Okay. So this is me like on the spot understanding the equations of the fucking slides, because before this I didn't know them either. So add n over 100 to this, so this is 2n squared over 50. So remove the 2, and this is n over 100. So our final result would be n squared over 50 minus n over 100 over n squared over 50 plus 2n. So that is our answer, I guess. So t is this.
Yeah.
Which approximately would be equal to fucking 1, because these n terms cancel out over the n squared if n is sufficiently large.
Yeah.
But they don't ask for an approximation, they ask for the exact.
Could you explain again how you got to how you derived the equation?
Okay, so how to derive the equation. So
Yep.
there's 2 parts of here that we need to know. Because the data locality, which is a horrible, horrible name for this. This isn't data locality, but okay, sure, /rand. The data locality is processing time over transfer time.
Yep.
Transfer time is quite easy. So what happens is I'm a fucking thread. I start off. I have nothing. I do not know anything. Where am I? What am I doing? Help. I need my part of the matrix to be sent to me, right? Because you need that part of the matrix. That part of the matrix is n squared over p.
How do you get n squared over p?
Matrix is n squared divided over p cores.
Okay, yeah.
Yeah.
And then plus n?
Plus plus n indeed, because this entire vector is n.
Yeah.
So if you look at that part, it is in here n squared over p plus n. So literally you can visualize this as large part of the matrix plus vector.
Gotcha.
So that's
It
the
makes
calculation. As for the other part, they wrote it in a very annoying way. I wouldn't have written it like that myself. So this is the way that makes sense to me. So to do the actual calculations, you need n squared over p multiplications, right? Because you have these numbers, and you're going to element-wise multiply all of them.
Mhm.
And then you need to add them all up, which is also n squared over p, except for the fact that there are not n additions per row, but n minus 1 additions per row. Right? So for n numbers, you add n minus 1 of them.
Y minus 1?
So if you have 5 numbers, you add them all together, you have four additions, right?
Oh, yeah, gotcha.
Yeah. So you have instead of counting the boxes here, so the numbers, you're counting the lines. So the amount of additions, if that makes sense.
Indeed.
And that is this much, which is n over p, times this much, which is n minus 1.
Mm-hmm.
So then you get n minus 1 over p. Work that out, and you get you get n over p times 2n over 2n minus 1, which is this.
Mm-hmm.
So that
Yep.
is how I got there.
Perfect.
Now to do the exact same thing for block partitioning, which is going to be a lot more annoying, because there's less things we can assume. So say we have bad gutter. Say we have a big matrix. How does block partitioning work? First of all, good question. Thank you, Jelle. Where the hell do I see this? So stripe partitioning, block partitioning. So so we have
So it's not just divided in like
in lines, it's also in
horizontal-
rows.
Yeah.
Okay, but luckily we know that p is 100, so we can work this out. So say you have yada 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 yada. Okay, well we'll use the exact same logic here. So the communication time. So okay, let's first show which part is it that we actually care about. I am a single processor. I care about this part. Oh, that's not a box. This is a box. I care about this part. And as for the entire matrix, or the entire vector on the right, I care about... Oh, fuck off. That doesn't even work? Bro. Okay, I'm gonna fucking kill whoever made this horrible app. So the only part we care about is this.
Mm-hmm.
Right? So, just to be clear, this is n over square root of p, and this is n squared over square root of p. Right? Because, well, no, this is not over square root of p. This is n squared over p. Yes. Because this entire matrix is n squared, we're dividing it over p processes, right?
Yep.
And the reason that the square root of p here is, so each line here, both the horizontal and diagonal is n over square root of p. So say we have 100 processes, like we have. This is okay. I'm gonna rewrite that because that's like very bad. So square root of p. Okay, so that's because we have this entire row, and square root of p is so say we have 100 processes, then we get 1/10 of the matrix row-wise and 1/10 of the matrix column-wise.
Exactly.
So here you get 1/10 of the entire thing. So for block partitioning, we need to p needs to be a perfect square, but you know, so be it. Communication overhead. Our communication is nothing more than n over square root of p plus n squared over p. Right? Because we have we need to communicate this part of the matrix plus this part of the matrix. I hope I'm making sense. The calculation part, so this is times tau the calculation part is this entire area, so n squared over b plus n over square root of b times n minus 1 over square root of b. So this one might look a bit difficult, but it's the same as I'm doing last time. I'm doing the height is n over square root of b, and the width is n minus 1 over square root of b. Yeah, I will finish. I will send the solutions. Bye.
Bye.
So yeah, the so that is the amount of calculations here. So if we work that out, that is n squared over b plus n squared minus n over b, which is equal to 2n squared plus or minus n over b. And this is the computing time, which is here expressed in. Wait, where is it expressed in? Yeah, it's expressed in C. So so for block, the actual time is so first of all the computing time. Yeah, so just the computing time, which we know is 2n squared minus n over b yeah, times c, but we know c to be 1 because it's given in the question. And the communication time is up here, n over square root of b. So frac n square root of b plus n squared over b. And then that entire thing over times 2. Actually, yeah, this is fraction over. Yeah, so I have to do 2 times. Yeah, because the communication time is twice as much as the other one. So, bit of a fucky equation, not gonna lie. But we can simplify it because since we know n, or since we know b. So b is 100. Square root of b is 10. B is 100. Recompile. Does this look any better? It doesn't even compile. That's probably because I missed a yeah.
Curly bracket somewhere probably.
Yeah, and it still doesn't like me. So that's because I removed the wrong one. So this fraction is completed here. This fraction is completed here. We start again.
Where, is there something?
I think I am missing another closing bracket, and I am missing it here. Recompile. Show me the money. Come on. Seem to be wrong because n over square root of b doesn't end where it should.
You're still busy? Goddamn.
Yes, I'm still busy. We are currently on exam number 3.
That explains. Yeah.
Yes, it does. Right. Okay, so that helps. Then we can simplify further, and we're on the second last question or third last question of exam number 3. Yes.
Once you're done, I'm gonna input about how transistors work.
Partner,
Really
sure. So we get this shit, and we multiply it inside of the brackets. Is there much more we can do? We can probably simplify this. Do I want to is the question.
Why did you do ×2 again?
So I do ×2 because it's the bottom part times the communication time. And the communication time, if we look at the question, takes 2 time units.
Ah, okay, yes.
Okay, I'm gonna be nice. I'm gonna fucking fully do this, even if it's just to get my fucking to get my calculation skills a bit on track, because I'm gonna have to do this on the test as well. So this 10n times 50. Okay, so I'll double the bottom part, so there'll be 100. There'll be 100 over 2n and 20. Recompile. And then we can multiply both sides by 100, which nicely cancels out. It's almost like I've set it up. That, remove these. Remove this. I just removed the 2, it should stay there. And it should close. Alright, that's a bit nicer to work with. And yeah, and I'll turn these two terms around so they're like line up a bit better. Right, so Tn is 2n squared minus n. Since I have to compare them, I'll also rewrite this to be proper. Frac n 100 over frac n squared 50 plus 2n, and this entire thing goes in a fraction. And this can go. I feel like I'm doing something wrong. I think I removed the n. Yeah, I did. N. Recompile. And I have a closing bracket too much. Fuck it. I'll fucking simplify this as well, so we can have a proper comparison of the two. Okay, so that's good. So now everything is over 100. So we can multiply by 100, clean this entire thing up. So it is 2n squared minus n on the one end, and the other end is n squared plus 200n. Right, okay, so for striped, we get 2 squared minus n. Okay, so yeah, if we look here, we see that this is always better, 100% of the time. In which case is it preferable? So I'm probably missing something, but if I had to look at it, I say no, it is never preferable. At least, because yeah, this is calculated, because no matter, because if you're even if your like processing time is very, very short, yeah, even if your like processing time is very, very short, or your communication time is very, very short and the rest is very, very long, I still don't see if why one would be better. Like that block one would be better.
The top one is the stripes, right? Like A.
The top one is stripes, yes. So stripes is dividing over a larger number.
Yeah.
And
Quicker time.
So are my calculations here? Did I fill this in correctly? Let me see. So this would be 10n plus n squared. 10n plus n squared. Yeah, okay, it's times 2, because of course it is. We just said that. And for the top one, it is... yeah, 2n squared minus n. Yeah, no, this is definitely correct. As for the other one, is it true that we get n over p is n over 100? So it's 2n squared over... yeah. So this top part is correct, yes. And the bottom part is n squared over p plus n. It's n squared over 100. Yeah. No, that's also correct. Okay. I'm gonna be clear. Unless I'm missing something, like performance-wise, block partitioning is never preferred.
Yeah.
I'm gonna just look it up. Block partitioning versus striped partitioning. Maybe it has to do with the fact that you have... Actually, no, there's one thing. So, block bar... No, even then not. I was thinking maybe if, like, your, you didn't want it to fit in... Or you wanted it to fit in cache, but, like, you have the same amount of data. So it's not like it'll change how whether it fits or in cache or not. Yeah, I agree. Okay, this is like literally a figure. Random bullshit, go. Control F, block. Yeah, no idea. Genuinely no clue why you would ever use block partitioning. It just seems worse. On my, yeah. Okay, well, whatever. Something we learned. Why is it, performance-wise, it is never preferred, if my answer is correct, which probably isn't. Oh, lovely, we can fucking... They did this, but instead of OpenMP, it's now MPI. Which sucks, but oh well. So, for begin verbatim. But I hope I haven't lost you all already. You still there?
I'm still here. I don't know.
Lovely.
Oh, it makes sense.
Okay, nice. Well, ignore the detailed criterion of the conversions check here. So let me just about. Okay, so this seems to be the way you tried this. Okay, so while it isn't converged, if I'm the root, while it isn't converged, if I am the root node or whatever it's called, I want the... So it's a grid. That's a weird way to write matrix. Okay, grid, sure. 301 to... So, okay, so the root node sends the edges and the other one. So this only works for two things, first of all, because this PID is 0 and PID is 1. So the other two just don't talk whatsoever. Oh, so the reason this doesn't work is because there's deadlock. Holy shit. Okay, good morning.
Oh yeah.
Yeah,
Just
okay.
have to.
Let's see what the question is, by the way.
Yeah.
Is the program correct? Efficient? Modify program correct, more efficient. The processors, compute row 1 to 300, value at the boundaries are exchanged after each iteration. Processor starts paragraph locally. Okay, so
Is it asking? Just have to fix the deadlock.
Yeah.
What is asking?
There's probably more to it than just fixing the deadlock, but this version is not correct, as it introduces deadlock by receiving on both threads and then sending on both threads.
You just change that over, right?
Yeah, it is. I will. For a correct version, and we go balabo and balaba, and even that I'm not even sure works. Oh no, it does, because it's sending 300 and then receiving in place 1. Although I'm not even sure. So hold on, what's this argument again? Oh, we're
So-
sending to 0 or to 1. Yeah. Okay.
Yeah.
So this is where it needs to look, how much it is, what you're sending, and then to whom you're sending.
Yeah. So but that's the receiving thing that you have now, right? So
Yeah. So oh yeah, I need to look down here. So all we care about right now is this. Like the update grid stuff, I don't believe we have to care
we're
about
sending.
that.
sending to
Oh, my indentation is wrong. Yeah, my indentation is wrong. That's why it doesn't make sense. So this goes in more, 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 this goes in more. Yeah, okay. So the update grid part is part of the yeah, it's part of the thing of the well, not converged. Okay, that makes a lot more sense. So we compile, look down there. So yeah, practically the only part we have to care about, like we shouldn't care about the update grid. All we have to care about is this, which is the exchange of variables. I feel like if this is C, we can just send, instead of looping over all 600 values, yeah, I'm actually sure about this. First of all, let's fix the order. So let's first send then receive. Then let's have a look at the at whether or not we're sending to the right place. So we're sending to 301, that gets received at 1. And then 0 gets put at 300. So I don't really understand the logic of doing this, because, like, honestly, that's one thing I don't get. Like, I don't get what the actual implementation is of these methods. So what I'm just going to do, I'm just going to assume that this is correct. Probably wrong, but I'm going to assume it anyways. Right, this ordering.
I think that's fine. Yeah.
Yeah. So what I'm going to do instead is I'm going to remove this entire for loop and go send from spot 0, from spot 0, from spot 0, from spot 0, send 600 of them. Because, right, like, there are 600 values in a row. Why in the hell would you wait for the entire, or why would you keep sending for every single value?
Yeah. Like, just send it as one message.
Yeah.
Yeah.
So yeah, I think that this will be a solution.
Yeah.
Yeah, not correct. It is, or here up here, it is also slow, as it is sending 600 single doubles. If you can also send doubles one at a time, when you can also send 600 doubles at once.
Yeah.
Love it.
Just a question.
Yeah.
Why, like, maybe this? Why would it work? Like, put the 0 instead of the I, because the I iterates over different numbers, right?
Yes,
So-
but so the reason this works is if you look at memory. So it depends on. It depends. I must admit that this depends on their implementation of if they're using C or Fortran. So this wouldn't always work, but I'm just going to assume they use C because C is the better language. So, say you have this is a bit much work for memory. Memory doesn't look like that. Let me just. So memory is like a line. And how it works is you have a line of addresses and yada yada yada. So if you have, so this is where the variable x points to. So x, so a matrix is nothing but an array of arrays. So this is x1. This is, or hell, let me just do it even better. X indexed at 1. X indexed at 1. X indexed at 2, X indexed at 3, etc. But what is here? It's not a value, it's a pointer. So x1 might point to here, x2 might point to here, x3 might point somewhere fuck off all the way at the edge, right? So this will be x1, 1. This will be x1, 2. This will be x13. This is like the layout in memory, right? So if we point to x10, I mean, sure, you should have started with 0. Oopsie. This is not Lisp. If you point at x10, you are pointing at the beginning of an array, right? X1 literally just is an array, and x10 is just the first element of the array. So x10 is just the first element of the entire row 1, which is stored there sequentially in memory. So if we say, look at point, grid 1, 0, that is, go to thing 1, element 0, so here, and then that ampersand means give me the reference to this, the references. So that's give me the reference to that field. So you are giving them the reference in memory, or the reference to this spot in memory. And then if you just take the next 600 steps, you're taking that entire array.
Yeah, okay, yeah.
Yeah, so that's what we're doing here.
Okay.
Right. Yeah, I think that is that then for this exam. Again, nothing to check, but I am quite confident that at least half of these are correct. Like, I would get a 6 with this, I think.
Yeah, sure.
So yeah, this went quite well for an open book exam that we did closed book.
Yeah.
Well, that's not true. I did look up the data locality, but okay.
It's something we need to look up anyway. So because
Yeah, I'm gonna have to learn that shit by heart. I mean, it's not that difficult. Like, now that I've used it like 4 times, I know that it is a communication or amount of calculation time over amount of communication times communication time, which makes sense, but it's just completely not what data locality should imply.
I had no idea what data locality is.
Yeah, because you haven't seen Lecture 7 yet.
Sure. Yeah.
Right, 131. We did all of the exams in about half of the time that we had, which is kind of funny. But also nice. It's kind of reassuring, if that makes sense.
We'll have enough time.
Yeah. It also means that I can go home and not miss my fucking bus, because the exam is like until what, fucking 11 or something. It's
Wait, does the bus not go after like...
It's 3 hours, by the way, the exam.
Yeah, I think we have 3 hours set out for the exam. Let me have a look. It is until 1 or until 9:30. So we'll be fine with the bus. So say I'm going from Makel Park at so tomorrow at 9:30, 21, and then 30. Say I'm going tomorrow, leaving, and I'm going to say Spijkenisse Centrum. Just random halt, definitely not where I would go.
Not that we're looking with you.
So
There
yeah.
you go.
Okay, so then there's actually quite some time. Like after here, I don't think there's trains anymore. Oh no, there's even a few more. Yeah. So
After 12 is when you get in trouble. But luckily, this is like
Yeah.
10, so
That you have
it is
options.
fine. Okay. That is actually quite good.
But
So
this shouldn't take,
Hmm?
shouldn't take that long back then. Should
Yeah.
take like maybe.
yeah. So if you have to travel for 3 hours, then you might get in trouble if you were to sit the full 3 hours. But otherwise, like, you're fine. And let's be real, we won't sit the full 3 hours. Right, I am gonna copy this and put it in the. I'll make a new folder and throw it in there. Answer 3 Delta text.
I think I'm gonna take a break for a bit and then
Same.
go
I'm
over.
gonna do this thing, called having dinner.
Oh yeah.
Also quite useful.
Yeah.
I'm gonna upload these 3 videos to YouTube, and I'll send the link in the homework announcements. So
Thanks.
I really want to thank you all for participating. I think if you weren't here, I wouldn't have learned half as much, and I also wouldn't have found the motivation to do the second 2 exams.
Oh no, it's
Mate,
likewise.
you are a fucking legend. Thank you.
You are very welcome, and thank you all for participating. And hopefully, I'll see you all at the test when we get that passing grade. Let's go.
Yes.
Let's
Let's go.
Bye.
Yeah.